Leetcode 33, search in rotated sorted array. It's a medium type problem, but it's definitely on the harder side, especially for problems related to arrays. Yeah, so it's quite hard for array type problem, and there are a lot of informations already contained in the title itself. So first of all, we have to notice that it's a sorted array, and once you get this information, you have to think about what kind of algorithms rely on the data being, on the input data being sorted. Yeah, and the next thing is that you have already here clearly stated what type of operation you are asked to perform, and this is a search type problem. And of course, there are many different operations that you can do on arrays. There is like insertion, deletion, and so on. But search is quite popular. And when it comes to array, there are two main algorithms that you can use: linear search and binary search. And in linear search, you are going to each element one by one. And in binary search, you can skip many elements, and that's why binary search is faster. And we will be talking about binary search in detail in this video. And the one thing that you need to have in order to use binary search is to have sorted input. Yeah, and because they are already saying this in the title, we can already like narrow down our options and be very sure that probably we are asked about binary search. And here is the description. There is an integer array called nums sorted in ascending order with distinct values. Yeah, so that's the input array linear structure with elements inside, and each element is a number, an integer. And additionally, we know that they are sorted in ascending order, meaning that the smaller numbers come first and then the larger ones, and each number is distinct, and there are no repetitions. Prior to being passed to your function, something happened before we get this nums array, is postedly rotated at an unknown pivot index k. Yeah, k is just an index position inside your array, and they will be explaining what they mean by this rotation. And k is between 1 and nums length, such that resulting array is the following. Yeah, so the first element initially would be nums on index 0, yeah, but in this case we have, after the rotation, the first element will be nums at index k from the original one. Yeah, the one that we don't know, that was prepared somewhere before we call our function, or our function gets called. Yeah, but then what do you have? K plus 1. Yeah, so the order is shifted. Yeah, but there is no like mixing up numbers in a random way. We simply shift by this rotation. That means simple shifting. And we will explain in a second in greater detail what exactly does it mean. And at some place in the array, you have the last element, n-1, and then the first, second, and so on. And for example, for such input array 0, 1, 2, 4, 5, 6, and 7, and 3 is missing here, this is okay. We just care about the ascending order. It might be rotated at pivot index 3. Yeah, and then it becomes such an array. Yeah, the 0 was moved here. Yeah, but after 0 we had 1, 1 is still there, then 2, 2 is still there. And what was at the beginning? The one that was after 2. Yeah, and then the order is the same: 4, 5, 6, 7, 4, 5, 6, 7. Yeah. It was rotated at pivot index 3, meaning it was rotated 4 times. Yeah, because we start with 0 index and we rotated it 4 times. Yeah. Given the array nums, after the possible rotation and an integer target, return the index of target if it is in nums, or -1 if it is not in nums. Yeah. So that's like the standard search operation. You have to find given key or given target in your array and return index on which it's placed, or -1 if it's not inside your array. Yeah, but the only complication, or the only like additional thing, which like I say only, but it's making the problem much harder, is that this array has been rotated and we don't know how exactly it was rotated. But still, there is a lot that we can assume, since they have mentioned all those constraints, like just integer, distinct values, and initially sorted in ascending way, but then rotated. And you must write an algorithm with O log n runtime complexity. Yeah, and I mentioned that there is this linear search and binary search, and linear search is ON algorithm, and binary is log n. Yeah, O log n. So this is another hint that we have to use binary search. Here is again the same array as in the beginning, and they want target 0. Yeah, and the output is 4. And that's the index. So 0, 1, 2, 3, 4. Yeah, and that's the index in the already rotated array, not the original array. The next is the same, I think, array, but this time target is 3, and 3 is not here, so we have to return -1. And the last example is like an array with a single number, just to remember that sometimes there are those edge cases that you can have, like in this case, the length is between 1 and 5,000, so you can have a single element, but there are no empty arrays in the test data. Yeah, so that is the only case that we have to worry about. And in this case, of course, output is -1, since 0 for sure doesn't exist in this array. So let's now copy this. And first we will be talking about rotation. Then we will talk a little bit about binary search itself. And then we will try to apply it in our problem. So here is the next. Yeah. So that was the original array that was sorted in ascending way, and it was rotated with the pivot at index 3, meaning it was rotated 4 times. And pivot I equals 3. And what happened between when we rotated 1 times, then 1 time, then 7 goes to the front, then second time 6 goes to the front, and one more time 5 goes to the front. Yeah, and finally we arrive at this, and this is the pivot at index 3. Now we can mark it here like this. Yeah, so that was our pivot, and after 4 rotations we end up with the following array. And now our task is to search in a rotated sorted array. So we are looking for a key or for a target value, and we've mentioned that this important keyword, and this is an important keyword as well. Yeah, search operation and sorted, meaning we should use binary search. Which additionally has O log n complexity, time complexity. Yes, so now let's try to figure out how this binary search works. And in a traditional or the standard binary search, we have sorted array, yeah, and we will have to adjust it for this rotation. So first, let's discuss the standard approach, where we create 2 variables, low and high, tracking indices, and each time they will be readjusted in each iteration, and we will be decreasing the range from within our array in which we perform the search. And why is it so? I'll explain in a second. So initially you start with low at the very beginning, yeah, at index 0, and high at the very end at index n-1. And then we check the middle value. Yeah, and the middle value is calculated by, first we have to calculate the index, and then using that index we take the value from the array. So the index, we get it in the following way: high plus low, or low plus high, doesn't matter, divided by 2. And now we have 3 options. First option is the best. So the value equals to the target. Yeah, and so let's maybe try to use some concrete target so it's not that abstract. Let's say that our target is 2. And in this case, we are done, we return, and in 2 other cases, we somehow readjust the range, and meaning we manipulate the values of the low and high variables. Other option is that the value is less than value at low. Not the value at low, then the target, and then we do something, and the value is greater than the target. Then we do something. Yeah, and let's now, before I write it down, think about together, and we'll think using, and we'll use this example to clarify everything. Yeah? So the middle point, of course, at the beginning is we have when we initialize low at the very first element and high at the very last element, that the middle element is the middle of the array itself, yeah, in the first step during our iteration. And now the value at this point is 4, yeah, and the target is 2, meaning that we cannot close or terminate at this point. We haven't yet reached the target, but we know a lot from this. We know that 4 is greater than the target. Then what do we do? Well, if it's greater than the target, meaning that for sure it cannot be on the right side, because all the numbers on the right side are already greater than the middle one because they are sorted. Yeah, that's how it works. So we know for sure that we will not find it here. We can then move the high end. Yeah, since all of this we already reject, and remove the high end here. And yeah, maybe let's leave it. I will right now like this, the green arrow, the middle one, and I will update it in a second. But now let's write it down. This is an important thing. If the value is greater than the target, this is our case right now, move or update high, and otherwise update low. Yeah, and low will be I plus 1, and high will be I minus 1. Yeah, why not I? Because we already checked that I itself also is not within this range. Yeah, and in the next iteration we continue like this. Okay, now we know that 1 is what, less than the target. Yeah, so we update which part? Low. That is our blue arrow, and we move it here. And now we have only one last element to check, and of course this is 2, and 2 is equal to 2, we can return. Yeah, so that's how binary search works. And as you can see, each time we reject half of the given range, meaning that in the end we have all log and time complexity. We don't go through each element, and as we would do in a linear search. So now let's think about the rotated version, because that's the main task here, rotated array search. And of course, the first two elements or the first two steps stay the same way. One thing that we can also clarify here or emphasize a bit, we did those steps not like single time, we do them multiple times in a loop, yeah, while low is less than or equal to high. And even this point stays the same. The only thing that changes is that we cannot just update low and high immediately, since we don't know exact place in which the array was rotated. Yeah, but we know some things, and let's clarify those things now. So instead of 2 options, basically we will have 4 options. And why is that the case? We will explain in a second. And here, started like this. The value is less than or equal to num set low or in another, maybe it will be easier in this way. Nums at low is less than or equal to the value, and that's the first option, is greater than the value. And here we have 2 sub options. So let's copy this. And if something, then we do this. If something else, we do that. Yeah, and we will clarify it in a second. And the same here. Yeah, so in total, there will be 4 options. But why is that so? So what can this condition tell me? If this green arrow is placed wherever, I can already say that either the part of the array on the left side is sorted or the part of the array on the right side is sorted. Yet there is no third option. How is it possible? Oh, let's say I place it here. At this point, I know that the left side is sorted. How do I know this? Because the number at low index is less than or equal to my current number. Yeah, it's less than or equal to 6. 4 is less than or equal to 6. That means I know for sure that left side is sorted. And it's not a guess. I know this 100%. And otherwise, I know that right side is sorted. Yeah, so if I move it here, 5 is greater than 4, meaning I know that the left side is sorted. Here, so left side sorted. Here, left side sorted. Here, finally, this one is less than this, meaning that I know for sure that which part is sorted, right side is sorted. Yeah, and this is really the case, and there is no third option. Either I know for sure that the left side is sorted, or I know for sure that the right side is sorted, and I can check it using this condition. Now, in these two options, we didn't yet use our target value. Yeah, and here we maybe do it like this and like this. Yeah, and I have again in each of those two, I have two options for each of those two cases. First option is that the value at numbers low is between that the target is between the low end and the middle. Yeah. If it is so, then we do this, and else we do this. Okay, like that. And this is for else. Maybe just else. Yeah, to not confuse you anymore. And the second thing, for the second part, we can check if it exists in this range. And we'll just run it through this algorithm in a second. Here, using the power of our brains and these beautiful drawings, or those beautiful drawings, and so those are the only four options. Only yeah, four is already a lot, but or five even if we count this one. But that's how the things get complicated with this rotation. So now what happens? We are at the first step. We initialized low here. We initialized high here. We checked the middle one, yeah, which calculated that the middle is at 0, 1, 2, 3, third position, or the third index, and the target is 2. Okay, so we check if the target value is equal to 7. Here we are at this stage first. No, it's not equal, so we continue. Now we check if the numbers at if the value at the very low end is less than or equal to our current value. Our current value is 7. Yes, it is, meaning that we know for sure that the left side is sorted. Yeah, and now we have two options still. Either we move the right position, or we move the low position, the right meaning the high position or the low position. Yeah, so when do we move the right position? If the number at the low end 4 is less than the target, yes, target is 2, and is less than the and is less than 7. And so let's maybe write it down here. In this first iteration, this would be following condition 4 to we try to check for 7. Is it true? No, it is not, meaning that the opposite is true, and we have to update the lower end. We update the lower end and move it here. And did we get closer to the target? Yes, we did. Yeah, target is here at the very end, and by changing this range, we rejected already half of the possible numbers. Yeah, we are no longer considering this part, and we know for sure that our target, if it exists within this array, it's not here. Yeah, so that's this, and now we can, of course, add the loop, and continue the iteration. So the next thing, we have to compute again the middle parts, the middle value, and now we are not yet at the target, but we will have to update blue, and in the third operation we will or in the third step of our iteration, we will have only one number to check, 2, and 2 is equal to 2, so we return the index, which is 0, 1, 2, 3, 4, 5, 6. Yeah. Otherwise, we return -1. Yeah. If we haven't found it within this loop, we have to return -1. And the same is true, by the way, here. Yeah. Either we find it within the loop or we have to return -1. So now the last thing that we have to do, once we have clarified and have a clear picture of all the possible options, we have to just translate them to Python. And let's start with the easiest part. So low and high equal to 0 and n -1. At the very end, we return -1 if we haven't found yet the value that we were looking for. And here is our loop. While low is less than or equal to high, we first calculate the middle by low plus high divided by 2. Now we check if we can, let's say it like this. If middle equals target, we return I. Otherwise, we have our 4 options. And what were those 4 options? The first one, nums at position low is less than or equal to the value, which we call middle here. And there's else. And inside here we have again 2 options. And this one goes here. Yeah. Either the target is within that range, meaning that this range is sorted, or it's outside, meaning that it's not sorted. So which one do we update here? Here do we update high? Otherwise we update low. And in this case we do opposite thing, low or high. Let's see if that's it. First 3 cases are okay. Now let's see. For all the cases we beat 100%, but our memory consumption is quite big. And it stays like this, so it's quite stable. Or probably we can do something in more compact way, but either way, the heart of the algorithm or the main idea stays the same.